What's the other equation, the equivalent equation to this? Instead of delta H, it's delta E. Delta E is equal to Q isochoric. And a bomb calorimeter is an example of a isochoric process. So what a bomb calorimeter measures directly is the change in the internal energy. Questions? So question number 2, the answer is the answer to question number 2 is who said that? Anna, you're right. You're welcome. Why? If system does work on the surroundings, W is negative. Okay, let's look at question number 3.
What was the answer?
The answer is E. Question number 3. The answer is C. The answer to question number 4 is the answer to question number 4 is answer is A. Okay, if you have an exothermic reaction, then the reactant is going to be there and the product is going to be there. Yes, Anna.
Why wouldn't the chemist take the point of view of the server?
So the
So it's saying like
what delta E is equal to Q plus W. That equation, the signs of Q and W are defined by looking at the system. The physicists, end up with Q minus W because they seem to focus on the surroundings. Actually, they seem to focus on one for one on the system and one for on the surroundings. Okay, so whenever you put in heat into the system, Q is W. So Q is positive. Jeez, sorry. Okay, when you put in heat into the system, Q is positive. When you do work on the system, then W is positive. So we are, as chemists, we are focusing on the system. Question number 5. The answer is B. I showed you a movie where you had a constant volume process and a constant pressure process. In the case of constant volume process, how much pressure volume work is done? What is the equation that you need to determine pressure volume work? We derived this equation in lecture number 17. W PV is equal to Angela minus P delta V. So how much pressure volume work is done in a constant volume process? 0. So in the case of a constant pressure process, pressure volume work is done, so some of that heat that you put in goes into the expansion work. That's why at constant pressure conditions, the Q is, or delta H is larger than delta E by 2.5 kilojoules per mole. For a constant volume process, all of the heat goes into delta E. Okay? But for a constant pressure process, some of the heat goes into the expansion that must occur when you go from liquid water to gaseous water. That pressure volume work is the extra amount that you talk about here as 2.5 kilojoules per mole. All right, let's go back to lecture number 17. Oh no, lecture number 18. Yes. The answer was C.
Aluminum metal is a very strong reducing agent. The flower pot contains thermite, a mixture of finely ground aluminum metal and iron-free oxide, plus a starter mixture containing magnesium metal. The reaction is initiated by igniting the magnesium metal ribbon. Some of the molten iron has flowed out through the bottom of the flower pot into the bucket of sand.
The reaction was so exothermic that it melted the iron that was produced in that reaction. Very, very exothermic reaction. All right, so let's go back to lecture number 18. We stopped at Hess's law. Hess's law is a consequence of the fact that enthalpy is a state function. So whether you go from here to here, or you go this way, it doesn't make a difference. Let me repeat that. Whether you go from A plus B to I plus J directly, or you go A plus B to C plus D to E plus F to G plus H and then I plus J, the enthalpy change is going to be the same. Or in other words, the sum of these enthalpy changes, note the fact that this arrow is pointing left. I was earlier talking about this reaction pointing to the right. So the sum of these enthalpy changes here must equal 0. Okay? This is, if you want to say, you can say this as conservation of enthalpy, just as you have conservation of energy.
Imagine if you could light a light bulb with a pencil. Today I'd like to share with you a material that's inside of a pencil that can do just that. I'm talking about graphene. Hi, my name is Anissa Ramirez. Welcome to my lab at Yale University. I'd like to share with you a Nobel Prize winning material that's found in a pencil that's going to revolutionize our lives. But first, what makes up a pencil? Well, there's the eraser, there's the wood. The part that I'm talking about is the part that you write with, which is graphite. Now, many people think it's made out of lead, but it's not lead at all. It's all carbon. Now, carbon is an old friend. You and I are made out of carbon. Carbon comes in many different forms or allotropes, each with different properties. There's diamond, which is one of the hardest materials that we know, and there's graphite, which is one of the softest. Both are made out of carbon. The difference is the way that carbon atoms bond in each one of these materials. In diamond, carbon atoms bond like this. Each carbon has 4 very strong bonds. In graphite, carbon atoms bond like this. Each atom has 3 very strong bonds within a layer, and then a weak bond between layers. Here lies the secret for that material that's going to help revolutionize our world. But first, let's talk about a few other forms of carbon. A few years ago, scientists found balls of carbon, or buckyballs. They also found tubes of carbon, or nanotubes. The ways that carbon bonds seems exhausting, but there's one more, and that's graphene, which looks like this. Now, in order to understand graphene, we have to go back to our old friend, graphite. Graphene is one layer of graphite. It's 1 atom thick. Now, how do you make graphene? What we can do is we can break this bond here. And we do that in pencils all the time. When we write with a pencil, we break this very weak bond and leave layers of carbon. Well, the Nobel laureates that found graphene did just that. Only they got a piece of graphite and they applied a piece of tape to it. And they did this numerous times until they got to a very thin piece of eventually graphene. And then they tested the electrical properties of the graphene, and they found that electricity passes through the graphene really fast, much faster than regular graphite. It's the one layer of atoms that allow electrons to move through this material super fast. Super fast electrons means super fast computers. Let's look at carbon in action. Here I have a circuit where we're able to light up a light by using graphite, just from a regular mechanical pencil. Let's try this together. Wow, that's pretty neat. Let's try something else. Let's just draw a line with the pencil and see if we can get the light bulb to light too. Let's try it again. That's pretty cool. Scientists think that graphene is pretty cool too. Because electricity moves through it so quickly, we'll be able to make computers with it that are very fast. Computers will be 100 times faster. Scientists are also interested in graphene because it's super strong. If you were to have an elephant balanced on a pencil, you would not be able to break a layer of graphene that's the thickness of saran wrap. That's really strong. That's going to change the way we make everything. So you see, the material that's at the tip of the pencil is about to revolutionize our lives. We're at a tipping point. Our old friend carbon has a few new tricks up its sleeve and will change our lives in ways that we can't even predict. I'm Anissa Ramirez. Thank you for joining me in my lab at Yale University, and I hope that you'll join us for another material marvel.
All right. Cool stuff. Very cool stuff. So what we're going to do now is look at the energy change, the enthalpy change when you convert diamond to graphite. Would you want to do this in a lab? No. You don't want to take your $10,000 diamond ring and convert it into graphite. Okay? But you don't have to do this because of Hess's law. Okay? We can use Hess's law and save ourselves $10,000. Okay? Here's the information that has been given. Can you use Hess's law and figure out the enthalpy change for diamond becoming graphite? So this is the first method of using Hess's law, and we're going to call this an algebraic method. What this means is that you can take an equation and multiply it by any number, positive or negative. And when you multiply an equation by any number, you have to make sure that you multiply the enthalpy change also by that same number. Okay, given that hint, can you try to work out this problem, please? Talk to your neighbor if you've already done it. So the answer is, who said that? Yes, Tiffany, what did you say? Negative 1.9. Can you think about it a little bit more before I work out the answer?
Was that the right answer?
That is the right answer.
I thought that didn't multiply anything.
You didn't multiply anything? Okay. There are, what you did can be thought of, what you did, I think, is you took equation 1, and from equation 1 you subtracted equation 2.
Yeah.
Okay? That's the same thing as taking equation 2 and multiplying it by -1 and adding the two equations together. Okay? You say potato, I say potato. Okay, everybody understands? Take equation 1 and from equation 1 subtract equation 2 and you get this equation here. And the delta H is going to be minus 1.9 kilojoules. Yes, Erica?
I don't understand how by subtracting you get diamond goes to graphite, because wouldn't it just be diamond plus graphite goes to nothing? Or
No. So you're going to have on the left-hand side, you're going to have carbon, diamond, minus carbon, graphite is equal to 0, if you want to say. Then it will be carbon, diamond going to carbon, graphite. All right? The oxygens cancel, carbon dioxides cancel. Questions? So this is called the algebraic method. And now we're going to use what is called, actually there's no name for it, it's just called method 2. It uses the concept of enthalpy of formation, and the method is best illustrated by this diagram here. What you're trying to figure out is the enthalpy change for a reaction, this red dark arrow. So you're going from reactants to products. The enthalpy change is what you're asked to calculate. What you're given is the enthalpies of formation of the reactants and the enthalpies of formation of the products. The reactants and products start from elements because by definition the enthalpy of formation is the enthalpy change associated with forming 1 mole of a substance from its elements in their most stable form under standard state conditions. That's what enthalpy of formation means. So you start with elements and you form either the reactants or the products, and that's the enthalpy of formation of the reactants, and this is the enthalpy of formation of the products. So the red arrow is equal to the big orange arrow minus the small orange arrow. Or if you want to put it in an equation form, the enthalpy change of the reaction is the enthalpy of formation of the products minus the enthalpy of formation of the reactants. All right, let's put that equation to use. Could you please do that problem? So I have gone through all of the questionnaires, the answers to the questions that you provided me. Thank you very, very much for your thoughtful comments. I scanned all of your questionnaires, but unfortunately some of you wrote so lightly that I was not able to get the image to come out correctly. So I need to work a little bit more, and then I'm going to post all of your answers so that everybody can see them. There was only one student whose questionnaire I was able to figure out, and that was because she put her name down. So I erased her name, and I want to post all of your comments. And some of those comments I'm going to act upon. Some of them I'm not going to act upon, and I will give you my reasons for why I am doing what I am doing. Okay? But I won't do that today because I'm not quite ready to talk about it yet.
So would you use the positive? I would just make it. Yeah, I would think so, because the product of the graphite was negative and then we
No, I think because you're using this one, and then what you do is you got it to this one.
Yeah, but I wouldn't know how to figure out what to do with this number.
You have to
Oh, is this not the ounce? No, it's not. This is
So the answer is,
Hi everybody, welcome. My name is Jennifer Gall and I'm the director of Dana Hall School of Music, and I just wanted to thank everybody so much for being part of this event.
sorry about that. The answer is positive 19.5.
Or is it, well, comparative basis, kind of like, if I compare
Yes.
do you not have to like take into consideration also the
So what is the enthalpy of formation of molecular oxygen? 0.
So then if it were anything else that wasn't like the natural thing, then you have to set with that?
Yeah.
Professor?
Yes.
So, we got the correct answer, but we're not positive that we can use the correct method.
Okay. All right. I'm going to take a short break and show you something, okay? Totally unrelated to this course. But I went to a performance yesterday.
That's the right answer.
Yeah, let's watch the whole thing.
That was my son,
Let's watch the whole thing.
11 years old. I cried yesterday. Okay. And maybe on another day I'll show you my daughter and my son playing a duet together. Okay, all right. Okay, so how do we do this problem here? So the enthalpy change for this reaction is the enthalpy of formation of carbon dioxide plus the enthalpy of formation of water minus the enthalpy of formation of propene. But you have to take into account the 3's and the 3's here. So delta H is going to be 3 times what is CO2? Negative 393.5 plus 3 times minus 286 minus the enthalpy of formation of propene is equal to minus 2058. Questions?
Wait, why is it that we don't account for the oxygen?
Oxygen, because the standard state of oxygen is O2.
Okay.
So the enthalpy of formation of molecular oxygen is 0.
Okay.
Sorry, Zoe, I completely forgot about your question. I got distracted by my... Have I answered your question now?
Yeah, I got it.
Okay, very good. Yes, Erica.
So are you ignoring the oxygen in the...
Okay, let's not ignore it. Okay, let's not ignore it. Does that make sense?